Kia ora, it's Bill here. I want to have a look at the StateMachine that I've got running this little system. I've got one button set up to actually change between states. So at the moment when I power on, I'm in state 1. You can see that from the LED. I've got the LED set up here to show which state I'm in. Press this, we go to state 2, which is the dim value, and that's been set by the trim pot value here. Press this again, it goes to max, so the LEDs are on max brightness. There's no PWM, it's just on max. And then press it again, and in this mode, it's in a sense mode. We're in mode 4 or state 4. And what happens is, and I cover over the LDR, you can see the LEDs get brighter. So what's happening there is that the pulse width is changing as I hover over this, and you can see there's the pulse width changing. So there's some simple relationship between the two. I haven't done much in developing any sort of smart transfer characteristic between the ADC reading and the value going into the output compare register for timer 2. So it's just a simple thing. So what happens in our state machine? So if we have a look at our state machine, we've got 4 states. We've got the light off, we've got the light in dim mode set by the pot value, trim pot, and then we've got the lights full brightness, and then we've got the sense, and then press the switch again, and it will go back round to state 1. So there's state 1, 2, 3, 4. Okay, and at the same time, I'm also sending some data out to TerraTerm, just so I can see what's going on there. Let me just connect TerraTerm, and we'll see what's going on. So at the moment, we're in light off state. You can see that. And I'll push this again, we're in light dim. So that's the value which has been fed as a pulse width value into the timer counter 2. And then we've got light on, which is just permanently on. And then we've got light sense, and you can actually see the readings changing as I hover over the LDR, make it darker. So we've got these different ways of monitoring. So these are different ways you can monitor which state your machine is in for testing purposes. So we can put some LEDs on and check the state. So then you know that you've transitioned. Most of the work for this state machine is done in the transitions. You can see that when it's in the dim mode and when it's in the light sense mode, it's checking the ADC. Of course, before it goes to check the ADC, we must set up which ADC it's looking at. In the light dim mode, we're going to be reading the trim pot, but in the light sense mode, we're going to be reading the LDR. So let's have a look at some of this code and see what's happening. So I'll go back to Atmel Studio. Here's our state machine. So you can see when we're in the light off state, all we're doing is we are checking to see if the switch is pressed. That's all that's happening in this state. When the switch is pressed, we change to the new state, and we do whatever transition setup is required to move to the next state, and then we wait for the switch to be released. If we don't wait for the switch to be released, it will immediately jump out of this while loop and go into the next one and see that the switch is still pressed. So we must wait for the switch to be released, and you'll find there's a simple little oops, down here, where's the switch release? Go to implementation. There we go. All we're doing here is we're waiting for the switch to go low, and we're delaying for 30 milliseconds in the process. So this allows any switch debounce to take place. Not a wonderful way of doing debouncing for switches and software, but a suitable one. It'll get us there for the moment. In the second state, we actually check the ADC, but what's happened is we need to know that which ADC is set and that all our timers are set up. We're using code which we've used previously before. So I want to go to look at light dim transition, go to that implementation, and that's down here. So the first thing we do is we set the ADC channel to read the trim pot. Show the state, which of course is the LEDs on the board. We set up the timer 1 and timer 2 prescale. Now, to stop a timer, what you do is you clear all the prescale bits for the timer, and it won't do any counting. So when we want it to start counting, we have to set the prescale again, and then I'm just sending this out. So now when we go back up to our state machine, so in this state of, let's just say that the LEDs are on dim. So in this state here, you can see that we are in light dim, we're checking the ADC all the time. So let's have a look at check ADC. This is code I've explained before. I won't go into it in much detail. So if there's an ADC conversion complete, then read the value, and here's my transfer function. Look at it, all it is divide by 4. So I'm taking a 10-bit value, dividing it by 4 to make it into an 8-bit value, and then I am sending that, and I'm putting it straight into the output compare register. So that's all I'm doing in terms of transfer function. So it's pretty easy for the and perhaps suitable for the trim pot, but maybe, you know, in the next state we'll look at. Let's have a look at the state is on is the next state. So to get to that, when we're in state light dim, we check the ADC. If the switch is low, then we turn on what happens if the switch is pressed, we're going to change to this state, and we go to light on transition. So let's go to that implementation, and we'll just click on this. So the first thing we're doing here is we're showing the state. Okay, so this is now in the lights permanently bright. I'll just move them out of the way. And what we're doing is, now here's something really interesting. In terms of these timers, these output compare registers are double buffered. So what that means is that here is your 16 megahertz going through your prescaler, divide by 32, and then it's going to timer counter 2, and then it's going to the pin which the LEDs are on. Okay, so now what we've got is we've got a comparator here, and we have an output compare register 2B. Okay, so when I write this value output compare register 2B of 255, it doesn't actually go into that until it's finished its current cycle. So if you imagine the counter over a period of time is counting from 0 to 255, it's counting up to 255 and then down to 0. Now, if we wrote a new value, let's see, here's the current value of output compare register 2B, then our pulse will look like this. So coming along. But if you change output compare register 2B to some other value, say up here or down here, then the pulse will no longer be phase correct, and also it'll sort of be a bit distorted, and you can get glitches in it. And so what happens is that the value that you're writing into output compare register 2B goes into a buffer first. And so it doesn't go straight into this register. What happens is it goes into the buffer, and then at this point in time, it chucks the value from the buffer into output compare register 2B. So to compensate for that in my code, what I've done is I've put a little delay in of 5 milliseconds. 5 milliseconds is completely over the top, because this is only 1 millisecond in time for my current values. So what I'm saying is that I'm putting the value into the register, but I'm putting it into the buffer over here. And then when it gets, and I'm waiting for 5 milliseconds, right, before I go on and disable my timers. If I don't do this, then this will just, it'll ignore what I've put into output compare register 2B. It will it will come back down to the end of the count, it will disable the timers, and my new value won't go into it. So I'm actually not going to get a full value in here. And you can play around with this and just see what's going on. If you don't put this delay in here, then it won't actually go dim, it won't go to full brightness. And exactly the same thing happens in this situation when I want to turn the LED off. In fact, I've only put a 1 millisecond delay in here for the period of the time to finish getting to the end of its count, and then taking it from the buffer into the output compare register. So that's what this little delay is for, and this is the reason why it's in the code. And then we disable it up here. So we have to wait for the timer to finish before we disable it when we're going into the light off or light max modes. And of course, then the other mode we're in is we're in mode 4. So let's go around to mode 4. That's there where the LEDs are driven by the pulse. The pulse of the LEDs is driven by the value of the LDR. And what's happening here is it's again light sense mode. All it's doing is checking the ADC and then checking to see if the switch is pressed. And if I go down to check ADC, you'll see it's waiting for the ADC conversion to be completed. All it's doing is this really simple transfer function divide by 4 to get from 10-bit to 8-bit. We could make a much nicer transition function here so that it actually, you know, depending on the light level, we might get a better range, dynamic range of movement of our LDR. So let me just look at that in my scope as I'm doing this. So as we hover over the LDR, I can't get to maximum brightness, and I can't get to maximum or minimum brightness, maximum dim. So I could design a much better transfer function, of course, taking into account the fact that this is a logarithmic process and not a linear one. I'll leave it to you maths guys to figure that bit out. So that's our state machine. Tricky little things in there to take account of were that when I'm going to the fully on and fully off modes, I actually had to wait for this count to finish before I could change and disable the timers. Okay, I think that's about enough explanation of the state machine, and as you can see, it works. Just go around to the 4 different modes, no problem. Excellent. There we go. Cheers.